Hi, welcome to the 10th session in group theory, third session in subgroups. In the last lecture at the end, what we did was, given a group G and element A in G, we, we wanted the smallest subgroups that contains A. We know it exists. Then we wanted a concrete description. We found the concrete description of the subgroup, the smallest subgroup, which that contains A, is the set of all elements of the form a to the power n, where n varies over z. Then we ended our session with the following question. Suppose G is finite, a to the power n varies over z. Z is an infinite set, right? So that is the subset of G, therefore it must be a finite set. Okay, what happens there? This is what we wanted to understand. So we are going to start with that today. Okay, let's start. Okay, so as usual, I forgot. Yeah, so G is a group and A is an element. Then if I denote H naught to be set of all elements a to the power n varies over z, this is the subgroup of G and it's the smallest subgroup. Okay, containing A, right? Okay, now question is, suppose G is finite, that is G is a finite set. Then this H naught, that's a subset of finite set, therefore this must be finite. Okay, we want to understand what it means. Okay, the answer to this, let me just check, I'm sharing the screen. Yes, the answer to this is, that means if this G is finite, H naught is finite, that means there exists an R and S, okay, integers. Let us assume R is less than S, so that a to the power R must be equal to a to the power S, because all of them cannot be distinct, right? A identity A squared a to the power something, and here A inverse a to the power minus 2 and so on. Okay, this set, okay, a to the power R, this is H naught is contained in G. This cannot be different. That means at least many elements should be equal, right? So let us, in particular, there exists two integers R and S, so that R is not equal to S, but a to the power R is equal to a to the power S. With our loss of generality, I am assuming R is less than S. Okay, is that clear? So therefore let us look n, or let us say m, equal to S minus R. This is greater than or equal to 0, strictly greater than 0, right? Right. There, that means let us look at a to the power S equal to a to the power R. So multiply both sides by the inverse of a to the power R, that is a to the power S into a to the power R inverse equal to a to the power R into a to the power R inverse. But remember, a to the power R inverse, we know from law of exponents, is a to the power minus R. Therefore this object is a to the power S minus R equal to identity, right? Now that means a to the power m is identity, where m is a natural number, right? Therefore let's look at the set of natural numbers k in n, so that a to the power k equal to identity. This is a subset of n and this is non-empty. Why it is non-empty? Because m belong to this, right? Therefore there exists, by well ordering principle, implies there exists an integer n, there exists a smallest integer, least element. It's actually the least element in this set. Okay, whatever the set quality is in S. Do you follow that? Yeah, call it n. Okay, so that means I have a naught is identity. Okay, let me start with a squared, a to the power n minus 1, and when I come to a to the power n, it is identity, right? Now, suppose my k is greater than or equal to n, then I can write this a to the k by divisional algorithm. I can write it as sum q times n plus r 0 less than or 0 less than or equal to r less than n. Yes. Therefore, I want to know what happens to a to the power n plus 1, etc., a to the power k. Right. Now, this is therefore a to the power k is going to be a to the power qn plus r, which is a to the power qn times a to the power r, and this is a to the power n to the power q into a to the power r, and this is identity to the power q into a to the power r, therefore it is a to the power r. But r is between 0 and n. Or if you want, 1 less than or equal to r, less than or equal to n. Okay, identity is also attained. You follow that? Therefore, there exists a least integer, okay, least such that a to the power n is identity. That means a to the power n, sorry, a to the power k, k is varies over z, is precisely the number of elements a squared, a to the power n minus 1, and a to the power n equal to identity. There, my h naught is this. Okay, pause, review, proceed. So, please go through that again. If G is finite, then there is a least integer n such that a to the power n is identity. In that case, H naught consists of exactly n elements. What are the n elements? Identity a squared, a to the power n minus 1. That's it. Have you understood? Okay, that itself is a subgroup. Okay, right. So, I will just introduce some terminology here. Okay, this n is called the order of A. Okay, is that clear? Yeah. So, A is called the order of, sorry, n is called the order of A. There are a lot of things we have to learn in the future sessions. Perhaps after this, I'll talk about order of an element in a group. In that, we will have a lot more discussion, examples. For the time being, what I want to assume is if G is a finite group, and then for any given A, there exists a natural number n such that a to the power n is identity. Okay, and what is this n? This n is called the order of the element A. And what is more interesting? What is n? N is nothing other than number of elements in the smallest subgroup H naught containing A. And H naught contains only identity a squared a to the power n minus 1. Okay, please go through, review. Okay, don't try to remember any of these things. Okay, you review. Whenever occasion comes, you keep reviewing. You will see that your brain sends this information to long-term memory, so it will be easier for you to recall. Okay, when you are when you watch my videos, your major effort should be to understand, think along with me. Don't worry about remembering, because I say a lot of things. It will be difficult to remember everything, but try to think along with me. Then you can see you will be able to recreate all those things on your own. Okay, let's go back. Okay, now let's look at some examples. Okay, suppose I have in C star is a group, right? Now let's take my A to be I. I is square root of one of the square roots of minus 1. Then we know I squared, which is minus 1, I cubed, which is I squared into I, which is minus I, and I to the power 4 is identity, right? Therefore, order of I is one usually denoted by O of the element A. this is equal to 4, right? But on the other hand, if I take a equal to minus 1, order of a is 2 because a squared is already 1, right? But suppose I have additive group here, right? Then start with any element other than 0. Suppose I start with n not equal to 0, then maybe I should stay with the a. Let us say a is an integer which is not equal to 0. Then I'll have a plus a is 2a, okay, a 3a. These are all a squared. With the additive notation 2a, additive notation 3a, whereas in the usual notation a cubed. So I can keep on doing, and here also I can do it minus a minus 2a and so on. That means the subgroup of a, okay, the smallest subgroup containing a is nothing other than all multiples of a, n times a, where n is a natural number, sorry, integer. That is what we denote by za, right? You understand? So the, here in this case we say order of a is infinity. This is a convention. Okay, good. So the, we will have a future session perhaps after this, order of an orders of an element.
Please specify what this order refers to. Knowing the content and independent sequence will help me structure the future session.
Element in a group G. Okay, there will be next session will be on this. Okay, now I now I want to do something which is usually again not done, because you can see many times how the elementary number theory is very crucial for understanding a lot of concepts in group theory. On the other hand, the group theory also explains some of the basic concepts in group theory. Okay, this is a two-way process. You can go this way, this way. This is a fantastic thing, which usually number theory people don't explain and algebra people don't explain this way. Okay, but it's this two-way process. I find it very interesting. Not only that, when you are going to learn ring theory, there is a notion of PIDs, principal ideal domain. Whatever you are going to do, you will see they have a lot more meaning in that. They will be highly significant when you go to ring theory later. Okay, now what is the question I want to ask? Now let us look at, I want to stick to only the set of integers now. So take Z additive group of integers. Now take two positive elements A and B. Okay, right? Now we have seen, okay, given any element, we ask for what is the smallest subgroup which contains that, right? So now I can ask, given two elements, does there exist smallest subgroup? What is the answer? The answer is yes. Okay, and we are going to find what it is. So let us start with a general question. Suppose A is a non-empty subset of G, okay, does there exist a smallest subgroup containing A? Answer is yes, of course, because let us look at H to be the H is a subgroup of G and A is a subset of G. Sorry, A is a subset of H, right? This is non-empty because G belongs to this, and therefore the intersection H, let me denote by HA, is intersection of H in script H. This will be a subgroup, and in A will be subset of this, and this is by definition the smallest subgroup. Is that clear? Okay, I am going fast. The logic is the same. PRP, HA is the smallest subgroup containing A. Okay, PRP. So one can give concrete description. HA but we will not do it now. Instead, let us take G equal to Z. We will look at a specific example under addition, right? And let's look at A and B, two elements and natural numbers for the time being, right? So my set A has two elements, A and B, right? Okay. Now let's look at HA. This is the smallest subgroup. Suppose H is any subgroup, so that A and B belong to H. That means A is contained in H, right? Then since A is in H, then any multiple of A, M is any integer, should be in H. Similarly, any n times B must also be in H. So, sorry, H. I said H, I wrote. Is that clear? Because this is something like A to the power m, and this is like B to the power n. And if n is in a negative integer, then it means B to the power minus 1 to the power n. We all know this, right? Now, H is a subgroup, MA is an element, NB is an element. Therefore, their group product, in this case, is a sum, MA plus NB should also be in H, right? This is true for every integer m and n. Is that clear? Therefore, let's look at this collection MA plus NB as m and n varies over z. Okay, look at this collection. Okay, yes. Now stop for a second. Stop. If you have gone through my ENT lectures, this set should ring a bell. Do you remember where you have seen it? The maths is fun if you try to relate. Okay, the moment you see this, you should say, I have seen it somewhere. Where is it? Okay, I don't want to say. I hope you, some of you remember. Let's go. Go ahead. Like in the last case, in the case of A in Z, okay, then we found NA. This collection as n varies over is already a subgroup, right? So here also we can say the same thing, because if I have M1A plus N1B and M2A plus N2B, both are in S, their sum will be M1 plus M2 times A plus N1 plus N2 times B. Therefore, that's also in S. And its negative will be minus M1 times A plus minus N1 times B. That is also in S, right? Therefore, S is already a subgroup. Subgroup containing A and B. Yeah. Now, where is it? This S is already in H. That means give me any subgroup H of G which contains A and B, then this subgroup S is already in H. That means S is the smallest subgroup. Okay, containing A and B. Right? This is the smallest subgroup of what? Of Z. But I know what are all the subgroups of Z. Therefore, there exists a unique D so that S is equal to HD. What is HD? This is D times Z or Z times D. All multiples of this. Yes, because we have seen if H is a subgroup of Z, then there is a unique A so that H is all multiples of A. Right? We had already seen this. There I call it Hn possibly. Is that okay? Right? Therefore, in particular, D belongs to this set. Belongs to S, which is HD, which is collection of all MA plus NB, M and N in integers. right? That means, and remember, M belongs to HD and N belongs to HD, which is S, right? That means D, M must be a multiple of D divides M, or M is a multiple of D. Similarly, N belong to this, that means N must be a multiple of D. Therefore, what do I know? D is a common multiple, right? So, now how many of you recognize what it should be? D must be the least common multiple. We have proved it in the ENT, right? By considering the set S, MA plus NB. Do you remember that? That's why it's always good to review. Okay, come back. So, and suppose now C is a common multiple of M and N. Sorry, A and B, right? Therefore, C must be some M times A and C must be N times B. Yes, it's a common multiple, right? Okay. Therefore, we see that my C belongs to my S. Since C belongs to S, which is HT, that means D divides C, right? Now, if C is also natural number, if it's a common multiple of M and N, right? And D divides that, that means D must be less than or equal to C. Therefore, D is the LCM of A and B, least common multiple of P or P. Are you thrilled, excited? See, in number theory, element number theory, we looked at this set, we did that. If you notice, there also we noticed these two objects. This S is a subgroup. Why did you do that? Addition of two elements from S is again an element of S, and the additive, the negative of any element, that is minus of any element in S, is also in S. There we did not use the word subgroup, but that's what happened. And we also already noticed, we didn't say that in element number theory. We said any subgroup of Z, additive group of Z, is set of all multiples of a single integer. Okay. Now just go through once over, review it. You will see how much you begin to appreciate, like, and love mathematics. Okay, very good. So that is the important thing. So about Z, let us quickly do what are the things we know. We know all subgroups. Namely, there are the form NZ or Z times N, whatever you want to say is multiples of N, which we called Hn. And the second thing we said is, give me any A in Z, the smallest subgroup generated by A is nothing other than A times Z or Z times A. And third, give me any two elements A and B in Z. I said A and B, but assume no. Okay, in Z, if you want, assume no. Then ZA plus ZB, okay, that is nothing other than M times A plus N times B, M N in Z, right? This is a set which consists of all multiples of A. This is a set which consists of all multiples of B. And when I write this set, this means take any arbitrary element here, any arbitrary element here. Yeah, that is, if A is a subset of Z, you must have seen in linear algebra also. B is a thing. When I write A plus B, what does it stand for? This stands for small a plus small b, where A is an arbitrary element of A and arbitrary element of B. Take some element here, some element here, add them and keep on doing that. That's what it means, right? And this we saw is a subgroup Z, which is LCM of A and B. Okay, pause, review, proceed. So now one more jargon or technical term I want to use. Now let us go to general group now. Any group. Okay, A is an element of G. Then we found A to the power n as n varies over Z is the smallest subgroup which contains A. Okay, this is usually denoted by algebra books by this angle bracket. Okay, less than, greater than. Okay, this is known as angle bracket. This, and one also calls this as a cyclic subgroup generated by A. Is that clear? Right? Now I want to ask you a few questions to make sure that we understand. Okay, suppose B is an element which is already in A. Then I have a subgroup, cyclic subgroup generated by B, and I also have a cyclic subgroup generated by A. Is there any relation between them? Yes, because this object is B to the power n. Since B belongs to A, cyclic subgroup generated by A, B is of the form A to the power k, right, for some integer k, right? Therefore, B to the power n is A to the power k to the power n. By law of indices, it is A power kn, therefore it belongs to A, right? Therefore, any element of the cyclic subgroup of B is an element of the cyclic subgroup of A. That means this is contained in this. Is this clear? P or P. Okay. Let us look at some examples. Okay. To have examples, I just want to step it up. So what I will do, I will try to do some, yeah. Let us look at Z4 under addition. Okay. What are the elements? These are the equivalent classes consisting of 4 elements where 0, 1, 2, 3 stand for the remainder. Remember, my 0 actually stands for remainder. The equivalent class of 0, this means all multiples of 4. 1 equal to this stands for this, when set of all integers when divided by 4 leave remainder 1, right? Please understand this. They are of the form 4n plus 1 and so on. Okay, right. Now let us look at what is the cyclic subgroup generated by 1. By definition, it is 1, 1 plus 1, 1 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. This is 2, this is 3, this is 4, therefore 0. Therefore, cyclic subgroup generated by this is actually Z4. Is that clear? Do you understand what I have done? Now let's look at the cyclic subgroup generated by 2. This means I should have a 2, then I should have 2 plus 2, but that's already 0. So this is the least positive integer. You understand what I am doing? I am looking for the least positive integer n such that A to the power n is identity. In this case, additive notation. Therefore, the least positive integer n such that n times A is the additive identity 0 here. Okay. Therefore, this consists of only 2 elements, 2 and 0. And this you had already seen, but let's make sure this. This consists of 3. 3 plus 3 is 6, which is 2. And 3 plus 3 plus 3 is 9, which is 1. Okay. And 3 plus 3, this is 4 times 12, which is 0. So, this consists of all groups Z4. Okay. Without computing, I could have shorted this. See, 1 belongs to this subgroup, right? Therefore, the subgroup, cyclic subgroup generated by 1 is a subset of this. But this is a subset of Z4, but this is already Z4. Therefore, I know it has to be equal. Do you understand the logic? Yeah? You like it? You keep thinking. Okay? As I keep saying, don't worry about remembering anything. Keep following, try to think, and the logic will be in your brain easily. Okay, right. Okay, now I want to look at some abstract example. Suppose G1, G2 both are groups, right? Now I have the Cartesian product G1 cross G2. What are these? They are the elements of the form A1, A2, where AI belong to Gi, I equal to 1, 2, right? Now let me denote any element A of G1 cross G2. A stands for A1, A2. Just for definiteness sake, let E1 be the identity of G1, E2 be the identity of G2, and E is the ordered pair E1, E2, right? Okay. What I want to show is there is a natural binary map, that is G1 cross G1, G2, this one, and G1 cross G2 to G1 cross G2. There is a binary operation. What is the binary operation? Very obvious. I have A1, A2, okay, and B1, B2. What should I get? I should get an element. But what do I know? A1 is an element of G1, B1 is an element of G1, therefore I can write it as A1, B1. And A2 is an element of G2, B2 is an element of G2, therefore A2, B2. Is it an element of G1 cross G2? Yes. So this is the binary operation. Now you can check A dot E is A, because A1, A2, E1, E2 by definition it is A1, E1, A2, E2, but that is A1, A2. Similarly, the other way around. Therefore, it is E is an identity, right? And you can also check its associative. This binary operation is associative, right? For example, A1, A2, B1, B2, C1, C2. There are so many brackets. I hope you understand this. Okay, I'm grouping them, right? This is A1, B1, sorry, yeah, A2, B2, and then C1, C2. That okay, that will give me A1, B1, C1, A2, B2, C2. And the other way around, you can do A1, A2, B1, B2, C1, C2. That will give me A1, B1, C1, A2, B2, C2. Both are elements of G1 cross G2. And is this element equal to this? That is true because associativity holds in G1. Is this element equal to this? Yes, because associativity holds in G2. Yeah. Therefore, this binary operation is associative. It has an identity. What is the inverse? Suppose I have A1, A2. Its inverse is A1 inverse, A2 inverse. Okay. It's easy to check. You do that. So this G1 cross G2 is called the product. Is called the product of product group. So what I have done is, if you give me two groups, I can generate a third group. Namely, it's a product group G1 cross G2. Yeah. Please review that. We are going to look at a very concrete example. And you see that it's not the standard textbook. I am doing a lot of things. Slowly you will see all of a sudden lot of significant things happen. Okay, right. Now let's take my G1 is Z2, G2 is also Z2. Both are under addition. Therefore, what are the elements of G1 cross G2? These are 0, 0, right? 0, 1, okay, and then 1, 0, and 1, 1. only 4 elements, right? G1, G2 cross 4 elements. These are the 4 elements. Is that clear? Right? Okay. So what is the addition here? Suppose I take, now let us call this as E, this as A, this as B, and this as C. Do you notice something very interesting? What is that interesting thing I want to consider? What is, remember what is the group operation here? Addition, right? That is 0, 1 plus 1, 0 is 1, 1. And suppose 1, 1 plus 1, 0, what is that? That is 1 plus 1, 1 plus 0, that is 2, 0, right? But that is 0, 1, right? And what are the other possibilities? There are 3, say 2. I want to say 3 elements. Therefore, let us look at 1, 1 plus 0, 1. That is going to be 1 plus 0 is 1, 1 plus 1 is 0. Did you see that? That means A plus B is C, and this is C plus A is B, and this is C plus B is A. That is, among these two elements, you add any two, you get the third element. And this is an abelian group. 4 elements are there. Okay. If you denote by E, A, B, C, so let us assume the group operation addition, then what happens? A plus A equal to B plus B equal to C plus C equal to 0. E. Maybe write it as 0. Right? A plus A is 0, 1 plus 0, 1. That is 0, 1 plus 1, which is 0, 0. You understand? And A plus B is C, A plus C is B, and B plus C is A. And abelian. Okay? Etc. Okay? Pause. Review. Proceed. This is known as Klein's 4 group. Okay? And this is an abelian group. Yeah? Now let's look at A. What is the subgroup of A? That means A plus A, we already know is 0. Therefore, it consists of only 2 elements, 0 and A. Similarly, subgroup of this is 0, B. And subgroup of C, cyclic subgroup generated by C. Okay? This is nothing other than 0 and C. You follow that? And these are the only non-zero elements. Right? And what is the subgroup generated by A and B? Okay? That means A must be there, 2A must be there, which is 0, B must be there, 2B must be 0, A plus B must be there, that is C. Therefore, it is nothing other than all of the group, Klein's group. Let us make it K4. I think that's a standard notation. I'm not very sure. Let us call it K4. Klein's 4 group. Yeah. So, the subgroup generated by any one of the non-identity element is a proper subgroup. It has only 2 elements. Right? Is that clear? Whereas we looked at Z4, we found that the subgroup of 1 is Z4 and the subgroup of 3 is also Z4. Right? But here in the Klein's group there are no such elements. Okay? So there is a, even though both Z4 and K4 are abelian, have the same number of elements, they seem to be different. because in Z4 I can find an element. Okay, the cyclic subgroup generated by that element is the full group. Okay, whereas in K4 I have an element, no element. Okay, there exists no element such that the cyclic subgroup generated by that element is all K4, right? Subgroup generated by A has two elements, B has two elements, C has two elements, and 0 has only one element. Okay. Now let's look at S4. In that I want to find a subgroup. Okay. So let me look at the let A equal to the transposition 1 2, B equal to the transposition 3 4, and C equal to the cycle decomposition 3 4. That is AB. Right. We already know, since these are disjoint cycles, AB is same as BA. We know that, right? And since these are all transpositions, I know that A squared is identity, B squared is also identity, and C squared is also identity, right? You see that? Yeah, therefore, if I look at H consisting of identity A, B, and C, this looks very similar to my K4. Seems to be the same. Okay, notation is different. That's it. Yeah. For example, Z4 under addition, this seems to be the same as I minus 1 plus minus 1 plus 1 under multiplication. Because what do? I send I to this I in here, that is plus or minus I plus or minus 1, and this Z4 I can send it to 1. Therefore, the other one I squared is minus 1, I'll therefore send it to 2. Then I cubed is minus I'll send it to 3. And I4 is 1, that I will send it to 0. Okay. So somehow they seem to be the same. Okay. Then symbols may be different, but it looks they have the same pattern. For example, suppose I take the cycle 1 2 3 4, then you see that it's a call it sigma squared you have, that is 2 3 4 1. Yeah. And sigma cubed and sigma to the power 4 is identity. It looks almost like additive group Z4. See, you follow that? Multiplicative group plus or minus identity and plus or minus 1 and plus or minus I and Z4 and this cycle 1 2 3 4, they all look the same. Okay, that is, it's like saying that if you want to know the income tax department wants to know cumulation, it has to know his PAN. Okay, and when for other operation like social kind of what you call benefits, etc., for various other reasons, I may need Aadhaar, right? But are they different? No, both represent the same person, right? It's something similar. I just prepare the ground for later concept. Don't give up. Don't give up. Okay. See, mathematics developed just because of this. Seemingly different objects we see, they show the same pattern. They exhibit the same pattern. We want to understand. We want to understand the structure. That's how maths developed. Okay, it's not just a definition, proofs, lemma, theorem, etc. So please understand. That's what I was trying to do. Okay, so I have another 15 minutes. Let me do something more. Yeah. Right. So I want to wind up subgroups. So let us do quickly some of the examples. G1, G2 are groups, then this is right. Now if you look at H1 to be this into E1 into G2 and H2, this is a subgroup of G equal to G1 cross G2. Why? Because any element of H1, AB belong to H1, that means A must be, it must be of the form E1 and B is any element in G2, right? Therefore, take two elements, the other element will be E1 B1, E2 B2. Okay, these are the elements of H1. Do you understand that? Sorry, U1. Any first coordinate is always E1. Second coordinate could be any arbitrary element. You understand? So what is their product? The product is E1 dot E1 and B1 dot B2, which is E1 B1 dot B2. So this is an element of H1. And what is the inverse? Suppose I have E1B, its inverse is E1 inverse, which is E1 B inverse, right? That is again of the form H1, because it must be of the form H1. That must be an element of H1. When it has to be an element of H1, the first coordinate always should be an element of the element E1. The second element should be an element of G2. Did I get it? Therefore, it's a subgroup. You follow that? Therefore, so can you think of? So I said this is a subgroup. Can you think of a second subgroup? I'm sure all of you got it, right? It is G1 cross singleton E2. That is also subgroup of G1 cross G2. Okay, right. That is one example. Second example, suppose G is any group and H is a subgroup of G. Fix an element, fix A in G. Then let's look at A inverse. What does it mean? It stands for A inverse, where H is an arbitrary element of H. You understand this? This is a definition. This is a subset of G. This is a subset of G. When does an element X belong to this? X belong to that if there exists A inverse. If there exists an H in H, so that my X is A inverse. So we are simply saying it's a collection of all elements of the form A inverse. Again, foundation course will help you to understand this better. Okay, any subset is defined by means of condition. Okay, therefore A inverse, if I use my foundation course, this set of all elements G in G, this is a subgroup of G, subset of G, so that there is H in H, so that my X is A inverse. So loosely we will write it as set of all elements A inverse. A in G, sorry, H in H. Okay, right. Now what I claim is if H is a subgroup of G, I want to claim A inverse is also a subgroup of G. It's very easy. Why? Because take any two elements x1 and x2 in A inverse. Then how does x1 look like? A H1 A inverse and x1 x2, right? X1 is A H1 x A inverse. X2 is A H2 A inverse. Therefore, this is A H2 A inverse. Now use associativity. Therefore, it's A H1 A inverse A H2 A inverse. But this is identity. Therefore, A H1 H2 A inverse. But H1 H2 are in H. That's a subgroup. Therefore, H1 H2 is an element of, call it H. Therefore, it's again of the form A inverse. Right? Therefore, given any two elements x1 x2 in A inverse, their product is also in AHA inverse. The second thing, suppose H is X is AHA inverse, N AH inverse. What is X inverse? That is AH A inverse inverse. That is A inverse inverse, H inverse, and A inverse. A inverse inverse is A, H inverse is some element and in H, right? This is an element in H. Therefore, it is again of the form AH A inverse. Therefore, it is in AH A inverse. Therefore, AH A inverse is a subgroup of G. This is known as conjugate of H by A. So we simply say we got AH A inverse, call it if you want H1, we got H1 by conjugating H by A. Okay, right. Now we will do some of the standard exercises. Usually I don't do exercises, but if you are a BSc student, you are struggling with abstract group theory, I just want to make you become comfortable with abstract thinking. That's why I want to do that. Okay. Now what I want to do is, you must have seen in linear algebra, if W1, W2 are vectors are spaces, W1 intersection W2 is a vectors are space, but yes, W1 union W2 need not be. So similarly, we want to prove if H and K are subgroups of a group G, H intersection K is a subgroup, but H union K need not be a subgroup. Okay. In fact, one can say much better. It's a subgroup if and only if one is a subset of the other. Do you understand that? Let's let us do it. 1. H is a subgroup of G, K is a subgroup of G, that H union K is a subgroup. Let me write this. If only if either H is contained in K or K is contained in H. Okay, this is the condition, right? Suppose H is contained in K, then H union K is K, that's a subgroup. Or if K is contained in H, then H union K equal to H, that's a subgroup. Therefore, this way implication is okay. Right? Now I want to prove, suppose H union K is a subgroup of G. Then I want to know whether this holds or this holds. Right? Again, foundation course is important. There are two statements. One statement is H is contained in K. The second statement is K contained in H. One of them must be true. So we want to prove it by contradiction. Assume H union K is a subgroup of G. Then I want to prove either this happens or that happens. To prove by contradiction, what does it mean? None of them happens. That is, assume H is not contained in K, K is not contained in K. So we prove by contradiction. Well, H is contained in K or K is contained in H. That is, therefore, what is that? Therefore, we assume, I am going slow because many people may not have gone through foundation course. Therefore, we are assuming H is not contained in K and K is not contained in H. If right, this also is not true, that means H is not contained in K. This is also not true, that means K is not contained in H. You understand? Now H is not contained in K. What does that mean? There is an A in H such that A is not in K. Similarly, K is not contained in H. There is a B in K such that B is not in H. Right? Now, remember, A is in H, B is in K, and H union what is it? H union K, yeah, H union K, right? Therefore, A and B both are in this, and this is a subgroup. If you want to call it L, A and B are in L, L is a subgroup. That means A times B must be in L. That is, A times B must be in H union K. Is the logic clear? Yeah, right. Now, this element is in H union K. What does that mean? That means either AB is in H or AB must be in K, right? Suppose AB is in H. Where is A? A is in H. Therefore, AB is in H and A is in H. That means AB is in H and A is inverse is in H. Okay, and this implies A inverse times AB must be in H because H is a subgroup. But that means B is in H. Do you see a contradiction? Because we chose B such that B is in K but not in H. Now suppose AB is in K, how will you argue? The same way, right? Now what will you do? You have to use A is not in K, right? So what will I do? AB is in K, B is in K, B inverse in K, therefore AB into B inverse in K, but that is A is in K, a contradiction. Okay, did you understand? Okay. There is one more thing which I wanted to do, but I think I have only hardly about 3 minutes. Let me stop it. Okay, but go through these things and let me warn you, what I am doing will not be the standard way any book or your teacher taught will be teaching. But let it not bother you. Okay, when you watch my video, simply focus on understanding, thinking along with me. After that, you read any book or listen to any lecture, you will see you understand it much better. In fact, you can think ahead of your teachers and book. That's a promise. But if you're sincere, yeah. I hope you enjoyed the lecture. We will meet again. Thank you very much.